Hello viewers, this problem is about a composite slab where the starting and finishing temperature of the walls are provided, and in between we are having different material of different thermal conductivities. Our task will be to find out the interface temperatures, right? Okay, so let us see the statement of the problem. A composite wall ID model is shown below and we need to determine the interface temperatures. For element 1, thermal conductivity is given as 5 watt per meter degree centigrade, and for the element 2, thermal conductivity is 10 watt per meter degree centigrade, and for element number 3, thermal conductivity is 15 watt per meter degree centigrade. So we are having three different elements, right? And the left end has a constant temperature of 200 degrees centigrade, and that our right end has a constant temperature of 600 degrees centigrade. Our task will be to find out the interface temperatures. So if we model this one using finite element method, three elements, it will be having four nodes: node 1, node 2, node 3, node 4. Four nodes will be there, and the distance between them equal to 0.1 meter, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. After calculating this one using ANSYS mechanical APDL, we'll show the results using theoretical calculations also, right? So without wasting time, let us start our analysis using ANSYS mechanical APDL. So this is the screen. First of all, we need to create a directory, and in that directory we need to save the work. So whatever file we are having, that we saved in the directory. We are not doing that one. And next to that, we need to change the title of this one, and let us change the title of this one as FA8. Okay, and to see that title, we can click on plot replot. In the lower left corner, it will be visible. Next to that, we need to start from preferences, and it is a thermal analysis. Okay, and after that we need to provide elemental properties, and that will come from preprocessor. So element type, add, edit, delete. Nothing is defined, so we need to add it. We are considering link 3D conduction 33 model with element type reference number 1. Okay, let us close it. Now real constant to be provided. From real constant we will provide the area of that slab. It is actually 0.1 meter square. So real constants, add, edit, delete, add. Okay, so the area of this one is 0.1 meter square. Okay, close it. Next to that, we need to provide material properties. In this case, we are having total 3 different materials with 3 different thermal conductivities. So 3 different materials to be taken from here, right? Material properties, material models, thermal conductivity we are considering, because in this case we are not having any kind of convectional heat transfer is not there. We are considering only thermal conductivity, right? So conduction will be there, isotropic, and first thermal conductivity will be for material number 1. First thermal conductivity is 5 watt per meter degree Kelvin. Next one, we need to provide another material, new model, and material ID is 2. We are providing the thermal conductivity of this one as 10 watt per meter degree Kelvin. Done. And the third material we can define from here. Material ID is 3. Okay, and thermal conductivity of the third material is 15 watt per meter degree Kelvin. Okay, done. Right. Now next to that, sections are not required because already we have provided cross section area from real constants. Now we need to model it, and while modeling we can create nodes. It will be easier for us. So create nodes. If we create node, in that case meshing is not required. So we are creating nodes. In active coordinate system, we can remember that total length of the slab was actually 0.3 meter. So 3 different slabs were there at a distance of 0.1 meter. So we'll be having total 3 elements and 4 nodes. First node will be created at origin. So apply, first node is made. Second node will be created at a distance of 0.1 meter. Apply. Third node will be created at a distance of 0.2 meter. And finally the last node will be created at a distance of 0.3 meter. Because total distance is 0.3. Okay, done. So 4 nodes we have created. In between 4 nodes there will be 3 different elements, and all these elements to be joined, right? Now we need to create elements, and for creating elements we are having 3 different types of material. So three different thermal conductivities to be assigned in this case, right? That will be done from elemental attributes. And in all cases, we're considering link 33 because one element type number was selected and material number will be different for each cases, and real constant also will be equal for each cases, only material number will be varying. First case, material number is 1. Okay, so auto numbered through nodes, we can connect node 1 and node 2. Okay, so first element is made, which is having thermal conductivity of 5 watt per meter degree Kelvin. Now the second one will be having different thermal conductivity, so we can use elemental attributes, and material number will be 2, and real constants also it will be same 1. Okay, so auto numbers through nodes, we can select node number 2 and 3. So element 2 is made, which is having thermal conductivity of 10 watt per meter degree Kelvin. Now the third element to be made, so we need to go to elemental attributes, and material number will be 3, selected. Okay, now auto numbered through nodes, you can select node 3 and node 4. Okay, and this is the third element, which is having thermal conductivity of 15 watt per meter degree Kelvin. So our material is defined perfectly, right? Next to that, we need to provide boundary conditions, that is loading, temperature at the left hand side and right hand side is specified, that to be provided from here itself. So we can go for load, analysis type, new analysis, it is a steady state analysis. Okay, so define load, apply thermal temperature on nodes, right? We're having fixed temperature at the starting and finishing point, and that to be specified at this case, right, on nodes. First node will be having temperature of 200 degrees centigrade. Select first node, apply, and temperature will be 200 degrees centigrade. Apply, and last one will be having temperature of 600 degrees centigrade. Selected node number 4. Okay, and temperature will be 600 degrees centigrade. Okay, done. Now we need to run it. Solution, solve current LS. If everything is right, it will show solution is done. Let us check it. Solution is done, so everything is perfect. Now we can see our results from general post processing. So close it. General post processing, plot results, can do plot nodal solution, degrees of freedom solution, and you want to see nodal temperatures, right? Okay, fine. So these are the temperatures at different nodes, and you can see at node number 1 temperature is 200 degrees centigrade, and at the last node temperature is 600 degrees centigrade. In between we are having different nodes, and the temperature at different nodes are specified, right? Now another thing you can see the results in the form of listing results, that will be better for understanding. So list results, nodal solution, DOF solution, nodal temperature. Okay, so these are the temperatures it is showing. At node 1 we are having temperature of 20 degrees centigrade. Second node we are having temperature of 418.18 degrees centigrade. Third node is having temperature of 527.27 degrees centigrade, and finally the last node is having temperature of 600 degrees centigrade. So here in this case maximum temperature is 600 degrees centigrade, and the interface temperatures are actually is 418.18 and 527.27 degrees centigrade. These are the temperatures we obtained. Now this temperature we have to show using theoretical calculations also, right? Before that we want to show the animation of this one. I want to show this model as a 3-dimensional one. So plot controls, tile, size and shape, and from here display of element should be on. Okay, this is the model. You can see it in a different way from oblique view. This is the model. You can see right hand side temperature is 600 degrees centigrade, and as we are proceeding in the left hand side temperature is less. Left hand side temperature is 200 degrees centigrade, and right hand side temperature is 600 degrees centigrade. In between at different locations you can see different temperatures are there, right? Now we can see the animation of that one also. Plot controls, animate, and you can see deform results, and we're going to see temperature from here itself. Okay, can make it forward only. See how temperature distribution is occurring inside this slab. Right hand side is having higher temperature, from that one it is transferring, and at different locations we can see different temperatures are there, right? Let us close it. Next to that, we need to show these results using manual calculations, right? So for that, we need to go back to our slides. Let us close it. So this was the problem. We have already done this one using ANSYS mechanical APDL, that to be verified with manual calculations using finite element method, right? So what we'll do is, let us go back to the next page and see. If we make this model, this is the finite element model. We're having three different elements. This is element number 1, this is element number 2, and this is element number 3. In between three different elements, we're having 4 different nodes. Node 1 is having temperature of 200 degrees centigrade, and node 4 is having temperature of 600 degrees centigrade. In between, we have to find out interface temperatures, that is temperature T2 and T3 to be find out. And thermal conductivity is also provided. Thermal conductivity of the element 1 is 5 watt per meter degree Kelvin. Second one is 10 watt per meter degree Kelvin, and third one is 15 watt per meter degree Kelvin. This is already provided, and cross section area is also 0.1 meter square. That is provided. Now what we'll do is, using finite element method, we have to find out the elemental stiffness matrix for different elements. Element 1, 2, 3, we have to find out K1, K2, K3. After finding all these different elemental stiffness matrix, that to be combined into a big one that is known as global stiffness matrix. After that, we need to work on the global stiffness matrix, right? Let us see the next slide. So using the specified parameters or specified data, we can find out K1, there is a stiffness matrix for the first element. K2, stiffness matrix for the second element. K3 is the stiffness matrix for the third element. In this case, you can see these are the locations. Now, after getting all these things, we have to combine all these different stiffness matrix into a big one that is known as global stiffness matrix, big K, right? Let's see that one. This is our global stiffness matrix K, right? So these C1, C2, C, these are very important. These are actually utilized to add all these different elemental stiffness matrix. After finding this global stiffness matrix, we need to connect with these equations KT equal to F, right? And we need to apply all the values like F1 is how much, F2 is how much, that to be applied here itself. F1, F2, etc. to be applied. And after applying all these things, we can reduce these equations. This is a 4x4 equation that can be reduced to 2x2 equations by eliminating the unwanted things. And finally, we can get the results of temperature T2 and T3. That can be seen from the next slide. Let us see that. So we can see that this matrix is reduced to 2x2 matrix. And finally, after calculating these two equations, we can find out that temperature T2 equal to 418.2 degrees centigrade, and T3 is the temperature at the last interface. It is 527.3 degrees centigrade. And first and last temperature was already provided. These are the given values, and what we got before in ANSYS mechanical APDL. So these are actually 418.18 degrees centigrade, and you can see here the second one is 527.27 degrees centigrade. So these are approximately equal values. Very little difference is there. ANSYS mechanical APDL values, what we got, that is completely justified or validated with these theoretical calculations. Okay. So with this one, we'll conclude our today's analysis. This was a very simple analysis of a composite wall. We analyzed this one using ANSYS mechanical APDL, and that was validated using theoretical calculations, right? So thank you so much for watching this video. Thank you again. Bye. If you are liking this video, please subscribe and share. And if you have any kind of doubts, please write to me. Thank you so much for watching this video. Thank you again. Bye. Thank you so much for watching this video. Thank you again. Bye.